Okay, well, welcome everyone. Thank you for coming on this really beautiful evening. I'm Mike Walter. I'm the director at the Earth and Planets Laboratory, and it's my great pleasure to introduce tonight's speaker, Professor Steve Parman. Steve got his bachelor's degree at Harvard and his PhD at MIT, and this was sometimes at the end of the last century. And
Last millennia.
The last millennia. Well done, Steve. That's right. Perfect. At the time, Steve and I had a lot of common interests, and we were both interested in rocks that are called komatiites. These are the hottest kind of erupted melts on the surface of our planet. And in fact, had the pleasure of going to Western Australia and hunting down these komatiites with Steve at one time. That was a great trip. Awesome. Lots of stories for another time.
I have some pictures. No.
I almost brought a piece with me, but I couldn't find it. So Steve, after his PhD, he went to the University of Durham in the UK up until 2008. I also was in the UK at the time, so our paths crossed again. And then he's been at Brown University since 2008. Steve has a lot of different interests. A few weeks ago, Steve said to me, Mike, it appears to me that since our early days together that you, Mike, have kind of gone deeper into the planet, whereas Steve has gone shallower and is actually looking upwards. And we're going to hear about some of Steve's interests tonight. Steve is interested in the crust of the moon and Mars and Mercury as well. Steve's here for a few months with us. He's a visiting scientist. He's a II fellow as part of our global visitors program. So tonight we're going to hear from Steve on new views of the moon. And if you stay around afterwards, we're going to set up a telescope on the knoll and you'll be able to see the most recent views of the moon. So we'll remind you again later. Steve, okay. Take it away.
All right. Well, thank you. Thanks for coming out. I hope if nothing else today, I share with you some enthusiasm about the moon and planetary science. I feel like when it gets reported in the news, like a little bit here, that's like, no, there's like amazing things happening, and maybe some of you, I was born in 1972. So the last person to walk on the moon was when I was born. So my life kind of is mapped out the exploration. Some of you may have been alive at that time and remember the excitement. And I wish we could have more of that excitement going on with, as we'll talk about, the Artemis program. And the new views on the moon, first I stole that from some of you in the science will know there's a recent volume called New Views on the Moon. And so what I'm going to do today, if I can make this work. Oh, no, I got this thing. It worked 2 seconds ago. Try it now. Oh, yeah. So yeah, I hope today to show you new views of the moon, both scientifically, kind of what we've learned since the Apollo era, kind of what's our modern understanding of the moon. We won't dig too deep into it. I won't try and get too technical, but please stop me if you have any questions. You want to get into the details, we can do that. But I hope to show you also kind of new views in the sense that we're going to go back to the moon and we will have humans on the moon in the next 10 to 15 years, and we will have literally new views of the moon. All right, so just to show you where we're going, so I'll spend a little bit of time talking about our current understanding of how the moon formed and evolved, and we'll do it in very broad brush, just a few concepts that will be useful in thinking about the exploration of the moon. Then talk just a little bit about what kind of questions we're working on now, like have we solved everything? Absolutely not. So otherwise I wouldn't be here. And obviously there's a million questions, but I'll just pick a couple, including one that I'm involved in. And that'll hopefully be about half the talk. And then the second half, maybe I can show you a little bit about what NASA's plans are for exploring the moon in the next 10 years or so. But again, as we go along, if you have any questions, this would be better as a discussion than me just kind of chattering on. So don't worry about stopping me if you have a question. All right, how did the moon form and evolve? This is kind of one of the things I do. I try to answer these questions with chemistry. You can also try to understand them with physics or a combination of the two. And the three kind of concepts I want to kind of impart to you, and maybe you've heard of some of these, is the idea that the moon was formed in a giant impact. And we'll talk a little bit about the evidence for why we think that. After that giant impact, we think the moon was completely molten, and the way it went from a completely molten state to a completely solid state, or nearly solid state, has really controlled its structure. Kind of what we see today is largely a product of that. We'll talk a little bit about cratering, because the other thing, when you look at the moon, mostly what you're seeing is the result of kind of the massive cratering of the moon over 4 billion years. All right, so step one, what is the evidence for a giant impact? Why do we think the moon formed in a giant impact? So one is, this is a movie, it's a computer model of this hypothesized impact between impactor, canonically kind of the size of Mars. It wasn't Mars, but the size of Mars, with a proto-Earth that was a little smaller than today's Earth. And this impactor comes in, shatters the Earth, and all those particles are pieces of the Earth and moon moving about. The color is temperature, and so the redder colors are hotter. And you can see particularly this material that's scattered about the Earth is quite hot, and this kind of leads to why we think the moon started molten. And it's just a few of these particles that will eventually come together to form the moon, something like that. All right, so why do we think that's a good model of the moon? So one is that the moon is moving away from the Earth in its orbit. So every month it gets a little bit further away, and in fact, we can predict, I don't know, it's like tens of millions of years, when it's going to be so far away that there will be no more eclipses. There'll be no more total eclipses, because it'll look smaller to us and it won't cover up the sun. Whereas like in the past, the moon was a lot bigger, and so the eclipses lasted a lot longer and were much more frequent. But if you roll the tape backwards, the moon moves towards the Earth, and it kind of gives this idea like maybe it came from the Earth. What this particular model is trying to solve is called the angular momentum problem. So go back to high school physics days. Angular momentum, right, is kind of the momentum that you have from spinning. This is like the whole idea of like moving your arms in and out, and you'll spin faster as a skater. If we have kind of models of how the solar system forms from dust moving around the sun, and we can estimate how much angular momentum, how much kind of spin the Earth or a planet should have. You know, how much spin Venus should have, how much spin Mercury should have. And the Earth has way too much, the Earth and Moon together have way too much angular momentum to fit these models. And so somehow we have to figure out, how did it get all this angular momentum? And so this model solves that, because that impactor coming in gives the Earth a little shove, and together they have this high angular momentum. So that's the geophysical explanation, or kind of the evidence for why we think there was a giant impact. There's then geochemical evidence why we think the Earth and the Moon were formed in a giant impact as well, which I won't go over in the interest of time. But basically, this is our simplest explanation. It's not that there aren't problems with this, and we can maybe in the question section talk about what are some of the issues with it. But it is consistent with our picture of the solar system, where we see that planet formation was kind of like a smash car derby. Like Venus spins backwards. Its rotation spins backwards, we think it got hit so hard by one of these giant impacts that it moved it backwards. We'll see on the moon, there's some really huge impacts, one in the South Pole. Mars, the whole northern section might be a giant impact. So the idea that the Earth was hit by a giant impact is very consistent with our view of the solar system formation. The only odd thing about it is it must have hit it just right to kind of spall off a little bit to make the moon. And we're the only inner planet that has a real moon. Mars has a couple of like captured asteroids, but so it was probably kind of a low probability event that formed it. Maybe just in passing, some people argue that it's the existence of the moon that let life form on the Earth because it's kind of stabilized our rotation a bit. And so some people have theorized that it helped life evolve on Earth by keeping the rotation of the Earth stable. All right, so next up we have the giant impact. Any questions about the giant impact?
Why is the leading edge of the impact so hot?
So when it comes in, I should look at it. When it comes in, it should be cold. When it hits the Earth, then you basically get friction. And it's just the friction and the compression that heats it up. Yeah, I don't know why it's so hot there. That's interesting. I don't know why that it's hot before it even gets to the Earth.
What's the current thinking about what was the impactor and where has it gone?
So we think it's combined with the Earth, and the Earth and the Moon are some combination of it. One of the things that we're still working on is we would think that if this impactor came in, it would have a different composition from the Earth. And we think that the Moon would mostly form from the impactor. So there's lots of lines of reason that would make us think that the Earth and the Moon should be kind of slightly different in composition, and they're exactly the same. And so this is kind of an existing problem, like a cutting edge problem in understanding the Moon's evolution, that the Earth and the Moon have so similar a composition is hard to reconcile with these models. So we're not quite sure. There was a recent paper that hit the news where someone modeled that the impactor is often called Theia, that Theia is actually kind of sitting at the core mantle boundary, and they've imaged it with seismology. I'm not totally convinced of that, but it was an interesting idea. But it's a great question. It's what a lot of people are working on. All right. So the next kind of paradigm in understanding the Moon and how we think about the Moon is the idea that after this impact, it forms and it's completely molten. Like the whole thing is molten. Essentially like lava. And so we call it the magma ocean. It's the whole planet is magma. And as it cooled and solidified, the key point here is it compositionally separated. So you can think about this as maybe like the cream that gets to the top of your yogurt or salad dressing, the oil and the vinegar separating. But basically the different compositional parts separate out. And I think I have a good, yeah. So here's kind of a graphic of that happening. So the red is the magma, and the little blue dots are crystals that are forming the magma. Most of them are denser than the magma, and they settle down. But right at the end, you'll see some white little balls forming, and they float to the top. And that's a mineral called feldspar or anorthosite or andesite. If it makes a rock, it's called anorthosite. So here it's in kind of stepwise. Here's the magma ocean, crystals settling down. And near the end, we get this flotation of crystals, and it makes a crust on the surface of the Moon. We call this the anorthosite flotation crust. And it may seem exotic, but you see it all the time. If we go out and look at the Moon with your naked eye or with the telescope, all of this white stuff we think is the anorthosite that floated out of the magma ocean. We don't see it on any other planet. It's unique to the Moon. As far as forming the whole crust, there is anorthosite on Earth, and our models for understanding the Moon's anorthosite come from going to places like the Adirondacks. Has anyone go to the Adirondacks? Yeah, so when you're walking around the Adirondack, that's all anorthosite. And it formed in kind of a similar way. It floated out of a big magma body, but not the whole Earth. Whereas here, we think this was a global magma ocean, and it all came out in a relatively short time. And part of this idea, or it came from samples that were brought back by the Apollo astronauts. So this is a piece of anorthosite from Apollo 15. And by analyzing its geochemistry, we can kind of pick apart this history. So it's one of the things we want to explore when we go back to the moon. We only have a very few samples of anorthosite from a very few places on the moon. One of the things we want to do is try and get samples from all around the moon and see kind of, does it vary in composition and age? Did it all happen at once? Did it happen over a long time? All right, so magma ocean, and then the third of kind of our the paradigms of how the moon formed and evolved is impacts. So on Earth, what sculpts the mountains and the valleys is rain and rivers and plate tectonics. On the moon, it's cratering, 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 and cratering, and then a few lava flows. So the whole surface has just been battered by impacts from giant impacts down to sand grains that are still bombarding the moon. On Earth, they burn up in the atmosphere, and we see them as meteorites or meteors, and they don't make it to the surface. But on the moon, there's no atmosphere, so it gets sandblasted by these meteorites like every second. It's just getting pummeled. And so we'll see the whole surface of the moon is this fine dust. We call it regolith. It's little pieces of rock, but it has this fine, fine-grained dust and glass little bits. That's extremely, it's one of the major problems, and some people would argue the major problem of exploring the moon and living on the moon, working on the moon, is this dust created by this pummeling. But what I want to just focus on now are some of these really big basins. We call it, they're so big, we don't even call them craters, we call them basins. Most of these are very old. So when the planets formed from dust, and then they formed bigger planets, and then bigger planets, there were dozens and dozens of small planetesimals floating around. And the final accretion to the last 4 planets was the accretion of these tiny little planetesimals. And so they left their scars. And the moon itself is recording one of these collisions, but once it formed, it got hit. And the biggest one is this one, the South Pole Aitken Basin, sometimes just called the SPA. And we'll see a lot of the missions, the planned missions to the moon, certainly the manned missions are going to the South Pole, and they will be on the edge of this South Pole Aitken Basin. As the solar system evolved, these planetesimals got swept up, and so the craters start getting, on average, smaller and smaller and smaller. A few of these big basins over here, after they formed, there were some basalt eruptions that flooded and filled them up. And so the other part of the moon, and go backwards, so the white is all anorthosite, and the dark color is lava, like something you'd see in Hawaii, not an explosive eruption so much, but what we call a flood basalt that filled these up. And sometimes you can see it pretty clearly that it fills up a basin, an impact. Not so clear over here exactly what the basin looked like when it got filled. But that's basically what you see when you look at the moon. You see the anorthosite, the white part, and the darker part is the basalt. And that's kind of it. How are we doing on time? All right. What don't we understand? Well, oh yeah, question? Yes.
So if you're being hit by a leak, you think it's the opposite.
Yeah, so this is a little out of my jurisdiction, but my understanding is they're so energetic when you have these impacts that it's not like you scraping something off. It like, even if it's hitting at like a 45-degree or 30-degree angle, it's more like a bomb goes off. Like there's so much energy that it hits and it explodes. The ejecta can kind of go off in the side, but the crater almost always is quite circular unless it's very, very oblique. Like I think once you get down to like 15, 10 degrees, and then you do see oblong craters. But for the most part, they're so energetic, they kind of just act like explosions.
You said there's no atmosphere on the moon, yet there's clearly gravity and some outgassing due to the basalt or the impacts. Are there no gases which are at that air will not be retained at some minute quantities?
Excellent question. This is what I work on. So in a couple of slides, I'll address that. But as far as gases, like as gaseous phase hanging around the moon's gravity is just far too low, and so they just drift off. The only reason we have an atmosphere is our gravity is, and the moon's is just too low. So if you're standing on the moon, you're essentially in the vacuum of space.
And what is causing them to drift off? The rotation of the moon? Centripetal
They're just their motion, right? It's the particle of atom, an atom, zooms around, and if it has a free path, it'll just go shoo, right? So the only reason like the air stays in this room is like bouncing off the walls and the gravity. So there's nothing to hold it.
But there is gravity, and
But not
if you
enough.
look at the Brownian motion
Yeah.
aspect. If there's a little force down and nothing forcing up, the Brownian motion is random.
Right,
And some would stay.
except this stuff on the top goes, right? The Brownian motion is collisions between atoms, and there's nothing to collide with on the top. The top atoms go, and then the next layer goes, and I'm kind of simplifying, but then the next layer, yeah, the one, so hold on to that thought. All right, actually, it's right here. I'll go back. All right, so a couple of questions. If the moon got so hot it was completely molten, how did it not lose all of its water? And we'll talk about there is evidence for water both in the moon and on the moon, and how much is there. And we'll talk about for exploration and living on the moon why this is such a critical question. And then, yeah, we'll talk, I guess, I don't remember if I put a slide in here. I was putting this together kind of on the fly today. I'm not sure I put one in here, but we can talk about why is the moon so asymmetric. You can see here, all the basalts, the crust is kind of thin on this side, but on the back side of the moon, it's completely anorthosite, and the crust is much thicker, and we're not totally sure why that is. Okay, so water in the moon. So this is the in the moon part of it. This is a remote sensing image from a satellite looking at the moon, not in visible wavelengths of light, but in infrared. And it turns out that a lot of molecules have the same vibrational wavelength as infrared light. And if you look in the right wavelength, you can see these molecules absorbing that light. And one of those molecules is water. And so what these areas are showing are places where the wavelength of light that corresponds to water ice, got absorbed. And so we think these are places, these red places, are where there's some water, and what we think it is dissolved in volcanic eruptions. Geologically, these red places look like volcanic eruptions. They actually look like what we would call pyroclastic deposits. These are volcanoes that are driven by expansion of gas, and they form into little particles, and then they make kind of basically a big pile of little glass beads, and we know this because we have samples of it. So the Apollo astronauts in Apollo 17 spent hours and hours walking around this kind of white and gray landscape, and you imagine if you walked for a few days and you only saw the colors white and gray, your amazement when you saw this big orange patch sitting on the moon. And they even have like the transcripts you can, or the recordings. They're like, oh my God, it's orange. It's orange. Did you see that? Yes, it's orange. So this is the orange glass. If you go to the Aerospace Museum, they have some of it there you can look at. That's about a centimeter piece of it. You can see it's kind of falling apart. And then this is a microscopic image. These are about 100 microns across. And these are little volcanic glass. You can think of it as like, when you open your soda can after it's shaken up, it kind of explodes. Well, instead of making a foam, imagine if you did that in a vacuum, you just have little droplets of soda going everywhere. So that's kind of what happened here. On Earth, you have the air that kind of holds in this process a little bit. So usually we don't get these kind of really fine beads like you get on the moon. But inside these beads, we've now measured these. A colleague of mine, Alberto Saul, measured the water inside these beads, and it matches very well with those satellite observations. So where did this water come from? Well, the lavas came from inside the moon, so they're evidence that there is still water in the moon. And this is a little difficult to explain with this giant impact model. So one of the challenges, one of the things we're trying to understand is how we can have this model that solves the angular momentum problem, solves the orbit problem of the moon moving away from the Earth, but also retains the volatiles in the Earth. We haven't figured it out yet. Still working on it. All right, so now I can get back to your question of gases retained. So as these glass beads are erupted, the eruption is driven by gas, exsolving from the magma, again, just like a soda can. The beads come out, they cool down enough to become glass, like you saw, but they're still traveling through space. In fact, they're still in the gas cloud. So momentarily, there is an atmosphere for maybe minutes, hours, as the volcano is erupting. And as the bead moves through the gas cloud and the gas cloud cools down to 800, 700 degrees Kelvin, the gas starts to condense back on the bead. And so when we look at the surface of the bead, the blue here is the bead. This white bar is it's still a bit mind-bending to me that we can do this. That's 50 nanometers, right? So, a millimeter is 1,000th of a millimeter. A millimeter is pretty small. 1,000th of a millimeter is really small. A millionth is a micron. That's almost unbelievable. And a nanometer is a billionth. And it's so small, we're actually getting down to the atomic level. So this is what's called an atom probe tomography image. And these dots are atoms. We actually have tools now that we can see the positions of individual atoms in samples. So what do we do with this? Well, here's this glass bead, that little orange thing. And then on top of it, we can see that green is zinc sulfide. This is condensing out of the gas back on to the bead. And then in these little red particles, which are like 5 nanometers, those are iron-rich sulfides that came out before the zinc sulfide. And we can map this basically thermodynamically, and we can tell the conditions that the bead encountered as it flew through the gas. So we can kind of map out how long that gas stayed around, but eventually it went away. So this is kind of what I do. I have a couple of students working on this. All right, so that's water in the moon. Evidence, so these are also volatile, zinc and sulfur, things we think may have gone away during the giant impact, and yet more evidence that the moon is not completely devoid of volatiles, as the giant impact hypothesis would kind of make you to believe. All right, so now water on the moon, this is what is driving more of the exploration. I don't know, maybe 20 years ago, there started to be observations. So this is the south pole of the moon. right? So we're looking up from, I guess, at the bottom of the moon from our perspective. And there are craters all over, and you have to think about it for a second. But if the sun is that way and the light's coming in, if I have a crater and the sun's coming this way, there are parts of those craters where the sun literally never shines. They're called permanently shadowed regions. And they only occur near the poles, because as you get off, then the light can get into the crater. So just near right near the pole, there are these permanently shadowed craters. And we look in there, again, with infrared spectroscopy. These green areas are where, again, we sense water. But here we don't think it's in lavas. We think it's actually some form of ice. At first, people were kind of excited to think maybe there's layers of ice you could ski on and dig up. Turns out that's probably not the case. Right now, we think it's probably kind of frost in between these grains within the soil, within this dust. But still, potentially enough there to be useful. And what do you do with water? Why is it so important? Well, obviously, you can drink with it, but you can also make fuel from it, right? So if you electrolyze water and split it into hydrogen and oxygen, you make rockets from that. In fact, the rockets I'll show, the big rocket that Artemis is going on is a hydrogen-oxygen rocket. So, what do you need when you go somewhere? You need fuel, you need water to drink. If you want to grow plants, even if you want to wash something, you have to bring water. If you bring it from the earth, pretty expensive to bring along. So this is like the most precious resource on the moon. And we'll see everyone wants to go there. So what is its distribution? Where did it come from? We think maybe as comets come into the inner solar system, once in a while, one will hit the moon, and it'll make, again, kind of a transient gas cloud, and that some of that will condense into solids in these permanently shadowed regions. And here, this is, we'll talk more about this. This is Shackleton Crater, and I think if you're going to put money on where the next people to land on the moon are going to land, it'll be here. And we'll talk about it in a second. But the ice we're talking about is down in there. All right, so what is the plan for exploration? Here is a picture. I think this might have been Apollo 17. They have the rover. You can see he jumped up. He's about 3 feet off the surface of the moon to show you, how low the gravity is. And again, you can see it's just all dust and rubble. I mean, if you think about that footprint, Armstrong's first footprint in the moon, it wasn't like he stepped on a rock. It was like he stepped on talcum powder. And again, I would point out, I was born when this happened. The technology, I was just down at Marshall Space Flight Center yesterday, and we went over to the Rocket Museum there. And I mean, it's incredible that it all worked. It was all like switches and analog. Just in the era of iPhones and AI, it just becomes more and more amazing that it worked. No.
The heat would dissipate from the crater after an impact back into space, and with this water cloud that's forming at the impact, how long would it take for that heat to dissipate and for that ice to form?
Yeah, I think that's a good question. I don't think we totally know that. I think it's one of these really out of equilibrium processes that people certainly model, but I think there's just a lot of how materials behave at those extreme conditions and far from equilibrium that make it difficult to model exactly. But space is not a great heat conductor, right? When you get your thermos that has the vacuum in it, it has the vacuum because the vacuum is not good. So it takes longer than you would think to dissipate the heat away from the surface. But we've got billions of years, right? So I think that's one of the things in all of this it's hard to picture like all this stuff I'm talking about, the craters, the north-to-side crust, that's like 4.5 billion years ago, 4.34 billion years ago. So there's been a lot of time for that to happen.
Do moons generally rotate or not rotate? What's the story?
They generally rotate with the planet. So everything in the solar system pretty much is spinning, right? The orbits and the spins, it all has the same kind of sense of vorticity. So if you got to Jupiter's moons, they're all kind of rotating. So the moon, it depends on how you look at it, right? So the moon, it's tidally locked to the Earth. So you could say, oh, it's not rotating, but actually it is, right? It's rotating once every orbit of the Earth. If it wasn't rotating, right? So if it was somehow, like if you guys are I think how this would work. Yeah, let's see. I guess I could go around the room, but if you're the Earth and I'm the moon, if I was always staying in the same orientation and not rotating, but going around the Earth, right? At some point you'd see the side of me. And then if I got back there, you'd see the back of me. So really the moon is rotating very slowly, right? You're always seeing the same face. So it rotates once every orbit. Exactly once. It's a resonance. Even as it moves further away. Partly probably due to the asymmetry, right? So the part of the moon that has the thin crust is kind of slightly denser is facing us. But yeah, it's tidally locked. And my understanding is it's always going to be tidally locked. I don't think it gets out of that. I think in the past it may not have been when it was closer to the Earth, but again, a little out of my jurisdiction though. All right. Oh no, am I going backwards? I see, I'm going backwards. All right, so again, I that's the science portion. We can ask, we can do more questions later. Let's move on to the exploration, right? And I can't impart to you enough about these meetings I sit on and how kind of exciting it is to hear, NASA is really doing this. They have, you were saying, they have contracts out to build some of the missions out to like Artemis 5, out into the 2030s. I would say that, lunar science and lunar exploration, after Apollo, kind of 80s, 90s, when Mike and I kind of came on the scene, 2000 is kind of, it was there, but it was kind of in the background. It's pretty low energy. And now it's just, all this activity, all the exploration, all the science that's going on. It's pretty exciting. So if you haven't heard, the successor to the Apollo program is the Artemis program. And it is mapped out to be as extensive, even more ambitious in some ways. And this is the rocket, or one of the rockets that's going to accomplish it. This is the SLS. If people get into rockets, but I think these are solid rocket boosters, and this is this hydrogen, oxygen central rocket, which actually has the same rocket engines from the space shuttle. They just took those engines and put them on here. But the capsule is way up at the top. You can see the arm at the top that goes over, and that's where the astronauts will be. And this is the Orion spacecraft that they'll be in. It kind of looks a bit like the Apollo capsule in many ways. It has some solar panels for energy. It's a bit bigger, and because the materials have advanced and the computers are a lot smaller, there's more space, much more space in there than the Apollo era capsules. But this is the Orion capsule, and we've already flown one. So Artemis 1 went up in 2022. This is actually a picture from Artemis looking back at the Earth and the Moon. The Moon looks as big as Earth just because of the perspective. There was nobody in this, and so Artemis 1 was a test run of the orbit. Artemis 2 is going to have these 4 astronauts. They've already been chosen. That's the crew. They're not going to land on the moon. They're going to go around basically in the same orbit that the Orion 1 capsule went around.
There's scientific reason for putting people on the moon?
Well, that's a huge debate, right? You ask 20 people, you'll get 20 different answers, right? Yeah. So scientifically, scientists I don't know, we're greedy, right? Like I want the answers now. And, at least at the moment, you put a geologist on an outcrop in an area or a robot. I don't know if you follow the rovers on Mars, right? I mean, these rovers, it's like they go like 10 feet and they take one picture and then they wait. And the next day they go like 30 feet and they take something. You kind of look at that. I'm not sure what that is. A human could do what Perseverance has done over the last few years, could do it in like a week and do it 100 times better. So at this point, certainly from a scientific, like a greed, like I want it fast, the humans will be able to do it much faster. Does it justify all the costs? The reasons we're going back to the moon are not, I would say science is not the top one, right? And it wasn't the top one when we went there the first time, right? The first time we went largely because of the USSR. And now we're going back, I would say, and many people would say, in fact, in NASA, because China's going. And so the big reason to go, they talk about like national prestige and inspiration of young people. And, I was inspired by it. And then science as well. So science is a third of it, but it's probably the smaller of the thirds to go back. But certainly having humans there will help, tremendously with the speed of understanding what we're seeing. So the way NASA works for really large missions is they have something called the decadal survey. And they get all the scientists to kind of say, what should we do in all of planetary science? And they recommend what the big missions are. And the number one rated mission of the last decadal survey was actually this really interesting combo of like robotic and human mission where they're going to land a rover. Let's go back. I'm going forward. So the humans are going to be here, but we're really interested in this. And so the idea is to land a rover here and have it drive along here and take samples and then bring them to the people. And what the people can do is look at what they picked up and kind of high grade it, which is extraordinarily hard to do robotically. So it's kind of, you get the best of both worlds where the robot can kind of stay on the surface for much longer, but then bring the samples to the people. They can high grade them and then bring them back when they go. So this is kind of where the advantage of having people. But yeah, certainly I don't think if it was just the science, I think it would have the value, but I'm not sure the government or the taxpayer would want to pay the billions of dollars to get those samples, but I would.
A commuting system do you foresee?
Yeah, well, so it's not foreseen. Like they have, I'm going to walk through the plan. So we have these, and so this is phase 1 of Artemis. So Artemis 1 has already flown. Artemis 2 hasn't flown. It was supposed to fly this year. It looks like now maybe 2026, where the first people will go around the moon. And then Artemis 3 is supposed to land on the moon. And you can see this space station. Basically, the ISS, the idea right now, the space station, they're going to decommission it and basically crash it into the Pacific Ocean. And then they're going to build another one called the Gateway, and they're going to build it close to the moon. And so the way you're going to get to the moon is that Orion capsule is going to go dock with Gateway, and then another rocket will go up there. They'll get into the other rocket to go down to the surface, and that rocket will look like this. So this is another interesting twist from the Apollo era, is now we have a couple of companies, many companies actually, but two big ones, SpaceX and Blue Origin, who are now have been given the contracts to make the actual vessels that are going to take the astronauts down to the surface. So this is SpaceX's rocket. Here are people. So these are gigantic. This is a gigantic rocket. This is Starship, version of Starship, if you follow that. Blue Origins is a little smaller, but you can see they're quite tall, structures. Part of that is this dust problem in that, if you tried to launch this and turned on these giant rockets right at the surface, you would kick up a giant cloud of dust. If your rockets are up near the top, and they just have to be relatively small rockets that fire, then they can lift you off the moon without causing a giant dust storm. So yeah, so that's phase one. So it involves building Gateway, and then the Orion capsule going to Gateway, and then one of those two rockets bringing the astronauts down and getting them back up. But there's no base or anyone staying on the moon for any extended time. And then the second phase is going to move towards having some sort of a permanent base, but it's not going to, if you have fantasies of like big buildings, it'll probably look more like this. And people have talked about it being more like the Antarctic science stations, where there will be somebody there all the time, but they will rotate. They'll probably stay there for a few weeks or a month, and they'll leave, and a new crew will come at the same time. But yeah, as you can see, Artemis 4, 5, 6, 7, and they have contracts. They're building these as we speak, I think out to Artemis 5. Right now, the timeline is 2029. That seems a little bit unreasonable if we go back. If you can see, I scratched it out here, but this says 2024. They were supposed to have done all this Gateway and everything. That's obviously has not happened, or has not happened in this year. As usual, these plans get made, they're pretty optimistic, and then the time's pushed back. But that doesn't mean any like critical things gone wrong. It just means it takes longer than they hoped. But these are, as far as, this is the plan. And these are the commercial rockets. This is SpaceX's rocket. This is Starship on top of it, which will look like that lunar lander. They're actually going to have to launch about 10 of these. Well, they're going to launch the lander rocket into space. Then they're going to have to launch about 10 of these to go up and refuel it. So it'll have enough fuel. So there's going to be some really interesting gymnastics going on. This is the New Glenn rocket. It hasn't launched yet, but I think it's supposed to launch this year. And what's really cool about these, if you haven't followed, both parts of this rocket are reusable. They're supposed to go up, do their thing, and land back. SpaceX already does this with their smaller Falcon rockets, and Blue Origins is supposed to do this as well. You think about those, those big Saturn V rockets that, from the Apollo era, those were one and done. Those are billion-dollar rockets that you launched, and then they went into the ocean. And kind of the new, in the new millennia, we're not throwing away the rockets. They're going to be reusable.
Where are the launch pads?
Where are they? Still Kennedy, Cape Canaveral is a big one. This one is in Texas, in Boca Chica, Texas. And I think New Glenn, I think this is launching from Florida as well. All right, so South Pole. I said, it's going to go to the South Pole. Why? Well, we already talked about water, and we talked about the water being in ice and permanently shadowed regions. But the other kind of funky thing about the poles is you say, okay, if I have a hole, then the sun will never get there. But if I have a mountain, potentially you have a place where it's in almost continuous illumination. And this is really important because any other place on the moon, remember, I'm doing this, but the sun's over there. And so the lunar night is like a couple weeks long, right? A month is one rotation of the moon. Half of that it's in daylight, and one side of it's in daylight, and the other half is nighttime. So a lunar night is 14 days, and it gets really cold. And actually, batteries and all sorts of things have a hard time surviving the cold, but also your solar panels don't work so well in the middle of the night. And so this survive the night thing is a real problem. And so the solution is to try to find a place where the sun shines almost all the time. And interestingly, at the poles, that ends up being right next to the places where the sun never shines. So your power source and your water source are the same place. But it turns out while the water, there's a lot of craters that probably have ice in it, the amount of land that has this like permanently permanently lighted or nearly permanently lighted, it's like a few football fields. So this is like the most expensive sought after real estate in the solar system, and everyone wants to get it. And right, so in some ways, it's a race between China and the U.S. to see who gets there first. And so I'll try and show you a couple of slides. That first image I showed were just the edge of the crater, that Shackleton crater, and we'll see just right on the edge there, and there's this little ridge. Out of all of this, the whole moon, that's the place to go. Right, so this is Shackleton. I showed that picture before. See those three little craters there? Keep an eye on those. So yeah, so just for scale, it's a big crater. This is the Grand Canyon. This is Shackleton. So one of the tricks is going to be, okay, if the ice is down here, how do you get down there and back up in this giant spacesuit? It's not like you're just going to traipse down there and pick up some ice and hike back. It's going to be a deal. All right, so let's see if this works as advertised. Yeah, so MIT is the best one I could find. This is going to be a movie of Shackleton crater over one lunar day. So here's Shackleton. Here's those three little craters. And here's this ridge. And if you watch, most of this will go dark for large periods, but here and here, more light. Not 100%, not all the time, but here you can see, right? Just there. And even that you can see the ridge is dark, but it comes back pretty quickly. Yeah. It's going to be a really weird environment to work in, right? Because the illumination, like the sun is going to be on the horizon all the time. It's never going to go up because you're at the pole, but it's super bright. And so the shadows are going to be black. But when you're in the sun, it's going to be like the brightest day. And so it's even just like walking around on the surface is going to take some getting used to. So it's, talk about new views of the moon. Like this is the new views that humans are going to have of the moon. This kind of black and white, super bright, super dark view. So you can more quantitatively see how much light an area gets. And so red here is almost 100%. Here again is Shackleton crater. Here are those three little craters. That little red area, that little red area, and that little red area. That's it. If you want to have your solar panel have light all the time, and so you put your base, let's say here, and then your ice is here. And so this is why we're going to the South Pole. Like you would never, it makes sense once you kind of think about it, but first why are we going down there? It's hard to get there actually just from an orbital dynamics. The reason the Apollo astronauts landed near the equator is just easier to do.
So will they have batteries that collect enough of this to basically keep it going around the clock?
So yeah, so you can bring batteries with you. So if you're going to be in a place that goes into lunar night, maybe you can bring batteries. You have to bring a lot, and batteries really don't like being super cold. The freeze thaw, the kind of contraction, expansion really is tough on them. So, yeah, theoretically you could bring enough batteries, but to last 2 weeks is a tough one. So the idea here is you don't really have to have batteries because you'll always have sunlight. But I'm sure they'll have some backup. That's right, exactly. So just power. You need power in some form, and right now solar is the one they're looking at. Yeah, and so here's those areas. I forget what this scale, but it was told it's a few football fields worth of real estate on the moon that everyone wants to go to.
The linear distance between those craters.
Between where?
Well, the three craters, how far apart are they?
That's a good question. Do I have a scale? It's like a sin. I always criticize my grad students. You have to put a scale bar. My understanding is this is kilometer, kind of a kilometer or two. But I should check that. Yeah, not far, but on the moon, not easy to move around. All right, and so then the last thing, once you're down on the moon, okay, you have your water, you have your energy. Is there anything else you can kind of live off the land? And this is just one example I thought really amazing. And there's 100 of these things going on. When I talk about the excitement, there's so many little companies that are working on these sorts of solutions. This turns out not to be a small company. This is Blue Origin. This is Jeff Bezos's company. But this is a solar panel, a little solar chip that was made solely from taking a scoop of lunar soil, a simulant. They dumped it into a little furnace. And the idea is that they could, from a scoop of regolith, you land something on the moon, they could take a scoop of regolith and print this solar panel on the moon. So you could land it, and it could start making solar cells there out of materials it lands on. And this is kind of what Mike and I do. Furnaces are 1 atmosphere furnace, but you basically have a furnace and you put a really huge electrical field across the molten material, and it reduces it, and it spits out pure silicon, which you can make the computer chip from. And this chip this is a demonstration. They actually did it. Not on the moon, in a laboratory. All right, and then I think just a couple of slides. It's you get more than 3 people in a room and you have politics. So, of course, we have the Artemis Accords, where other countries have signed up to be partners with the U.S. and are contributing in many different ways. But you can see also who's not here, right? So China is not part of the Artemis Accords, and they have their own plans for working on the moon. So, I've kind of mapped out the U.S. plans. China is actively doing this, and there's a race. NASA really sees it as a race that it's of strategic importance to get there before China does, and China thinks of it in the same way. So there is a real race on, very much like in the Apollo era. All right, so I say back to the moon, and one of my colleagues is like, no, forward to the moon, forward to the moon. So this is for my colleague Carly, forward to the moon. Yeah, it is happening, and I think this year you'll really see. I think there's 6 more missions to the moon this year, and every year afterwards there's going to be 6, 7 missions of various types, and punctuated by these big Artemis missions coming up. All right, that's the end, and I'm supposed to show this slide, and thanks for listening to me.
Thank you so much, Steve.
Okay.
And don't forget, we're going to go look at the moon
Yes, we have a
with
question here.
telescopes.
I don't know if this fits in your field, but we just saw the solar eclipse. The moon is smaller than the sun, but still we saw it covering the whole sun. How does this happen?
Yeah,
Why?
it falls under, coincidences happen. So we happen to live in just a perfect time that from our vantage point, the moon and the sun are just about the same size. In fact, it's not always the same, right? The moon has an elliptical orbit. So an annular eclipse is when the moon is a little bit further away, it looks a little smaller and actually doesn't cover the moon or doesn't cover the sun. And so you see a little bit of the sun. So you only get the full eclipses, the total eclipses, when the moon is a little closer to us. Again, back in the past, the moon was much bigger, was much closer, and it looked much bigger to us. And so the eclipses were even more total. But in the future, as the moon recedes, it's going to look smaller and smaller, and at some point, there's going to be no more total eclipses. So we just happen to live at the right time.
Because in some places they have, you started in Mazatlan, Mexico, in
Yes.
Texas, in Arkansas.
Right.
You see the whole.
That's right. It was completely covered. And, it turns out that sometimes coincidences happen. And right now, there's no reason.
There's a magic ratio. It's, what is it? The Earth is 400 times larger than the moon, and the Earth is 400 times farther away
I see.
from
Yeah,
the
yeah,
sun.
that makes sense. Yeah.
And so it just happens to be that the sun in the sky
Right.
is the same size as the moon.
I think one of the things in geology, whenever, whatever your field is, whatever your job is, I think it kind of, you do something that most other people don't do for a long time. It kind of warps your brain. And I think for geology, that's time, right? And, for the rest of humanity, like mountains are permanent things, right? But to a geologist, they're like clouds passing along the surface of the earth.
That's
And
profound, Steve.
there
I
we
have
go.
to remember that
But
one.
like you think of the size of the moon, like the moon's always the same size, but from a geologic perspective, it's like, no. A billion years ago, it looked much bigger. The sun was much dimmer back then as well. So
Maybe from the perspective, the sun looks smaller.
the sun would have looked dimmer back in the past. Yeah.
Question over here.
Yeah.
Do you want to do?
I'll run the box.
Oh,
Yes. Oh, this is.
And I guess there's online questions too, or maybe not.
there's a couple.
Okay.
Well, you covered most of them.
Okay.
You mentioned earlier that the composition of the moon is strikingly similar to the Earth. In what way is that? Because for me, from a layman's perspective, I don't get it. I mean, you have the Earth iron core, you have granite. So in what way is it similar? Because it sure doesn't seem that way to me.
That's right. So there are some how to even approach this. So the moon and the Earth have had very different histories. So to the extent they have the same composition, the fact that the moon had this magma ocean, it fractionated and then it froze. So we're really seeing back, the surface is like 4 billion years old, 3.5, 4 billion years old. On the Earth today, most of what we see is a couple 100 million years old, like the ocean basins. And then the continents, yes, very small pieces that go back a couple billion, and just a couple of tiny pieces like Mike and I went to see that are older than that. And so partly the difference that you're seeing on the moon and the Earth is the different histories, not so much their composition. There are some slight compositional differences, but what we really focus on are isotope ratios. Isotopes, again, going back to high school chemistry, so we have like hydrogen, and hydrogen can have one proton and no neutrons, or can have a proton and a neutron. We call that deuterium. And if it has two neutrons, that's tritium. If I'm boring you to death, feel free to close your eyes. It turns out, a lot of atoms have various isotopes. And what's interesting is isotopes, they're the same element, so they behave chemically the same. And so as they go through reactions, they don't really get fractionated from each other that much. And so they're fantastic in tracing things that we want to see through all these chemical reactions, through the magma ocean separating, through plate tectonics. Turns out isotopes see through all these confusing processes. And when we look in the isotopes, the Earth and the Moon, I mean, it's like I could show you 20 isotopes, isotopes of different elements, where the Earth and the Moon are like the same. And it's like, well, how does that happen? But yeah, the elemental compositions, especially when we're just looking on the surface, those are difficult to interpret sometimes. But the isotope ratios, and this is, again, one of these things that is a huge revolution in our field. I mean, since Mike and I started, the ability to measure isotope ratios out to 6, 7, 8 decimal places in the ratios, and how we can use that, not just in geology, but like forensic science, tracing things like one use of it is wines. So you buy your really expensive wine, it's from this one little area, but of course, like, you know, the person from there might want to mix in some cheaper wine from someplace else. You can tell where the grapes were grown from their isotopes. And so it's kind of the same with the Moon and the Earth. They look like they grew right in the same field, like they're grapes from the same, and it's hard to understand that.
Well, it's related. I was gonna ask that question. But I'm
Continuing on with this topic, you said that they have different histories, that they came out of the same event. They have the same isotopes, but they have different histories. And that explains why there's such enormous difference between the two. Can you say more about that? I mean,
Sure,
why do
sure.
they have different histories?
Yeah. A lot has to do with their size and how fast they cooled off. So the Moon, it's a much smaller potato than the Earth. And so it cooled off very quickly 4 billion years ago. And so basically the processes stopped. A lot of the processes we see on the Earth that are active are heat driven from the internal heat of the Earth. The Moon loses its heat. Mars is small, it lost its heat, and the planet dies. And the Earth is going that way. In a couple billion years, dead. So we're big enough that the Earth has stayed warm inside, and things are moving around, and that brings, you know, material up and lavas and plate tectonics. The Moon, that stopped billions of years ago. And so when you look up at the Moon, you're kind of seeing like a time capsule. In fact, we don't really have many samples on the Earth older than, let's say, 3.5 billion years old. Some people think the best place to look for 4 billion-year-old Earth rocks is on the Moon, because if you had a big impact that ejected samples, they might be collected on the Moon's surface and may still be laying there for us to find.
That's why you need people on the.
That's why you need people to see that. Exactly.
Steve, you also answered one of the questions on.
Okay.
What I was going to ask is, why is there no volcanoes on the Moon? And that's it. Cool.
So yeah, I mean, it is and isn't. So what's interesting is, by this model that the Moon is small, we think it should have died off like 3.5 billion years ago. The Chinese equivalent of NASA landed on the Moon a few years ago with a mission called Chang'e 5, and they brought back samples, volcanic samples that were 2 billion years old. Much kind of young. I mean, we kind of expected them to be that young, but it was still kind of like, whoa, it's kind of young. So there is this question of like, what allowed some volcanoes to keep going on the Moon as long as they did?
Well, I think we'll stop it there. We've been a little bit over.